Welcome to This Explainer. Today, we're peering behind the curtain of one of the absolute most fascinating engineering disciplines of our time, natural language processing, or NLP. You know that crazy modern magic where our machines seem to miraculously understand us, anticipate our thoughts, and even generate incredibly human-like text? Well, how does that actually work? That's exactly what we're going to unpack today.
To really grasp how powerful this technology has become, just consider the absolutely wild story of the Google LaMDA controversy. Recently, a Google engineer was tasked with evaluating a conversational chatbot model called LaMDA. He ended up having these incredibly deep, detailed conversations with this AI about rights and about personhood, and he was completely captivated. In fact, he genuinely believed the AI had become sentient. It's a phenomenal hook into our topic, right? Because it perfectly highlights the sheer persuasive power of modern language models. They've gotten so staggeringly good at imitating us that they can literally fool the very creators who build them. Okay, let's dive into this. Here is our roadmap. 1. The illusion of sentience. 2. What can NLP do? 3. How does NLP work? 4. The deep learning era. 5. Controversies and stochastic parrots. And finally, 6. Start your NLP journey. Section 1. The illusion of sentience. Demystifying the AI magic. So, transitioning from that mind-blowing illusion of a conscious machine to reality, we have to look at the objective math. Fundamentally, natural language processing is not magic at all. It's a rigorous engineering discipline. It evolved from computational linguistics, sure, but its goal isn't just theory. It's about building actual technology to accomplish useful tasks by manipulating human language. And it really splits into two overlapping areas. First, we have natural language understanding, or NLU. This is all about semantic comprehension, actually figuring out the intended meaning behind a text. Second, we have natural language generation, or NLG, which is the machine generating brand new text. Basically, one reads and the other writes. Section 2. What can NLP do? The everyday magic. And this brilliantly illustrates how this practical toolkit silently powers the everyday digital tools we often just take for granted. Notice the distinct tasks we have here. When social media platforms like Facebook need to moderate hostile intent, threats, or hate speech, they're relying on toxicity classification. When Gmail keeps your inbox clean by doing a binary classification on unwanted emails, that's spam detection in action. And when you travel and use Google Translate to automate translation between languages, you're relying on heavily advanced NLP machine translation. These are not abstract concepts. They're the literal filters and bridges of our modern internet. Another absolutely fascinating application is summarization, and there are two totally distinct ways machines do this. Extractive summarization is basically like a student with a highlighter. The system scores each sentence in an import text and simply extracts the most important existing ones to form a summary. Abstractive summarization, though, that is much more advanced. It paraphrases the original text to produce a brand new, human-like summary. It totally mirrors the way you or I might read a long document, process the meaning, and then write a fresh abstract entirely from scratch. Section 3. How does NLP work? Peeling the onion. So the massive question here is computers fundamentally only process numbers, right? So how on earth do we get them to read text? Well, the answer lies in data pre-processing. Before a model can do anything, it has to chop human language down into a format a machine can digest. Step 1 is tokenization, splitting a large text into individual words or fragments. Step 2 is stop word removal. We just discard uninformative filler words like the or a because they don't really add much actual information. And finally, step 3 is lemmatization. Now, I know that sounds like heavy jargon, but it's a highly relatable concept. It essentially analyzes the morphology of a word using a dictionary to find its root base. Think of it as taking words like universities or universities and chopping them down to their bare foundational roots. Now, what's really interesting about this extraction process is the evolution of the math. Traditionally, we used a bag of words approach. It literally just counts the number of times each word appears in a document. But that has some major flaws. A meaningful word like apple might get totally drowned out if the word very appears 50 times. Contrast that with TF-IDF, which stands for Term Frequency Inverse Document Frequency. This is mathematical elegance. It weights each word by its importance in a specific document, but then it actually penalizes the word if it's too common across the entire collection of documents. This helps the machine realize that rare, specific words carry the most meaning. But you know, a real game changer came in 2013 with Word2Vec. This completely revolutionized feature extraction. Instead of just counting words, Word2Vec uses a neural network to learn high-dimensional word embeddings. What this means practically is that if words appear in similar contexts, they are mathematically mapped close together in a virtual space. It finally allowed machines to capture context and the invisible relationships between words. Section 4. The Deep Learning Era. Milestones in Machine Learning. Let's move to the next phase and see how this builds, because walking chronologically through these milestones is honestly awe-inspiring. Back in the 1960s, a system called ELIZA tried to fool humans using basic pattern matching, which were essentially glorified parlor tricks. Fast forward to 2011, and IBM's Watson actually wins Jeopardy using open domain question answering. Then, as we just saw, 2013 brings word-to-vec and contextual neural embeddings. But the true paradigm shift? That happened in 2017 with a paper famously titled "Attention is All You Need." This introduced transformers, an architecture that relies on a self-attention mechanism to process all words at once, rather than one by one. This incredible, parallelizable power is literally the bedrock of the AI boom we're living through right now. And to fully grasp the breathtaking scale of what those transformers enable, just look at this number: 175 billion. That is the massive number of parameters in the Generative Pre-trained Transformer 3, or GPT-3. The sheer computational scale and breathtaking size of modern generative pre-trained transformers are exactly what allow them to write original prose with human-equivalent fluency. Section 5. Controversies and Stochastic Parrots. The Price of the Magic. Now, we have to be objective here. This breathtaking scale does not come without a very real cost. Think about it. When you train a massive model on uncurated data scraped straight from the web, it naturally inherits society's flaws. A famous 2021 paper actually warned of stochastic parrots. These are models that blindly repeat and amplify historical biases and toxic language. There's also a pretty severe environmental toll. Training these massive models has a massive carbon footprint. Then we run into the black box problem, which is a total regulatory nightmare. Deep learning models are essentially unexplainable. We don't strictly know how they arrive at specific outputs. And finally, the sentience fallacy, which we discussed earlier with that LaMDA story. It's the very real danger of mistaking highly coherent, statistically probable dialogue for actual, true consciousness. This leads to some very strong criticisms from within the field. For instance, writer Gary Marcus famously called deep learning-based NLP nonsense on stilts. His perspective is an important one to understand. He warns that these incredibly sophisticated algorithms mislead users into assuming machines possess advanced reasoning capabilities that simply do not exist. In this view, they are, at their core, incredibly advanced pattern matchers, not thinking beings. Section 6. Start your NLP journey. Wielding the magic responsibly. Despite those controversies, the potential to profoundly impact the world in positive ways is absolutely massive. If you want to get involved and safely wield this powerful technology, here is a concrete, step-by-step roadmap drawn directly from the experts. Start by laying a solid foundation. Learn basic mathematics and learn to code in Python, which is the absolute standard language for NLP. Then don't jump straight into transformers. Implement traditional algorithms first, things like naive Bayes and logistic regression. Once you've got the basics down, move up to studying neural networks using popular deep learning frameworks like PyTorch and TensorFlow. And finally, stay updated. Read research papers on archive.org and subscribe to industry newsletters like The Batch. So the absolutely crucial point here is that no matter your current background or level of expertise, there are perfectly structured resources and specialized courses available right now to help you master these techniques. You don't have to be a wizard to understand the magic. You just have to be willing to keep learning. Which leaves us with one final, profound thought to consider as we wrap up this explainer. When you look at the breathtaking speed of this engineering discipline, ask yourself, are we truly on the verge of creating systems with real underlying reasoning, or are we simply building ever more sophisticated stochastic parrots destined to just mirror our own language back at us? It is a fascinating question and one that the next generation of engineers, perhaps some of you, will help answer. Thanks so much for joining me, and keep exploring.